Hello, everyone, and welcome back. Over the last few sessions, we have taken a methodical journey through open channel flows. We started with the Froude number and wave speed, and then explored the energy and the specific energy diagram. We mastered the Manning equation for uniform flow, and we learned how to analyze the gradually varied flow, those slow, smooth changes in water surface profiles. But let's be very honest, as exciting as the gradually varied flow is, it's well gradual. But today we are going to look at the other end of the spectrum. We are going to look at the rapidly varied flow or RVF. So this is where the depth changes dramatically over a very short distance, where the term dy over d of x is on the order of 1 or even approaches infinity. So this is a world of hydraulic jumps or water crushing over the weirs of sluice gates shooting out supercritical jets. So these flows are complex, often turbulent, and sometimes even unsteady. But they are also incredibly important for energy dissipation, flow measurement, and controlling water levels. So today we will cover three main types of rapidly varied flow, which are the hydraulic jumps, flow over sharp crested and broad crested weirs, and the flow under the gates. So let us begin. Let us start with the most important and interesting example, which is about the hydraulic jump. So this is a step-like increase in the fluid depth that occurs over a very short distance. So as we can see this particular photo, it's a wall of the turbulent churning water. How does it form physically? Physically, it happens when there is a conflict between the upstream and the downstream conditions. So imagine a sluice gate that produces a fast, shallow, supercritical flow downstream. Further down the channel, maybe there is an obstruction or a mild slope that requires the flow to be deep and subcritical. So the flow cannot transition smoothly, it has to jump. The hydraulic jump is the mechanism that actually makes this abrupt transition. So let us analyze it. We will consider the simplest case, a horizontal rectangular channel. We make a few key assumptions over here that the flow at the sections 1 and section number 2, just before and just after the jump, is nearly uniform and one-dimensional. The second one assumption is that the jump itself is so short that we can neglect the wall shear stress. Friction on the channel walls is negligible as compared to the turbulent mixing inside the jump. So now we apply our fundamental tools. First with the continuity equation as represented over here, and second one by the momentum equation. Since we are neglecting the friction, the only forces are the hydrostatic forces at the sections 1 and 2. Now, if we remember that the pressure is hydrostatic, so the force on the vertical face can be represented as gamma times the depth of the centroid multiplied by the area, or but for the rectangular channel, that's half of the gamma multiplied by y square multiplied by the b. And we can also write subsequently the momentum equation, and we can simplify it by using the simplest gamma form as gamma is equal to rho g and cancelling the common terms over in this particular equation. And after some algebra and using the continuity to eliminate the v2, we arrive at at a quadratic equation into the depth ratio, which is y2 over y1, and solving it gives us the classic hydraulic jump equation, which is represented by this particular equation as y2 over y1 equals to half times the minus 1 plus under root 1 plus 8 Froude square equation. So here the this particular equation is showing us that the depth ratio across the jump depends only on the upstream Froude number. But if we know how fast and shallow the water is coming in, we can predict exactly how deep it will be after the jump. So this is the physical meaning of this particular equation. Now look at this particular figure. It plots this depth ratio as a function of Froude number. Notice that the curve only makes physical sense for Froude number greater than or equal to 1. But if the Froude number is less than 1, this equation gives a ratio less than 1, meaning that the depth would decrease. but we never see a reverse hydraulic jump, meaning that the water does not spontaneously jump from deep to shallow. Why? Because of energy. Let us look at the energy equation across the jump as displayed over here. So the term HL in it is the head loss. This loss is not due to the wall friction. We neglected that. It's due to the intense turbulent mixing and dissipation inside the jump itself. So the water churns, eddies form, and kinetic energy is converted into heat. So if we calculate the head loss from our equations, we found out that the Froude number is less than 1. The head loss would be negative, and that would mean that the flow gains energy over here, which violates the second law of thermodynamics. So a hydraulic jump can only occur when the upstream flow is supercritical. If nature's way of violently shedding excess kinetic energy to make a supercritical flow possible. So an example problem as displayed over here, water coming off a spillway is moving at 18 feet per second with a depth of zero point 0.6 feet. The upstream Froude number is 4.1, which is highly subcritical. So using the equations, the depth after the jump is calculated out to be 3.19 feet. The head loss is 2.26 feet, and the power dissipated is a whooping 277 horsepower, 277 horsepower. So that's a tremendous amount of energy that would otherwise score the riverbed downstream. Engineers design stilling basins specifically to force the jump to occur in a controlled location, protecting the channel from erosion process. So, in this slide, we also include a fascinating table that classifies the hydraulic jumps based on the upstream Froude number. So it's not just one type of jump, the structure changes dramatically. There are five different cases over here for Froude number between 1 to 1.1 and 1.7 is if the Froude number is in between 1 and 1.7, it's a weak undular jump, make more like a standing wave. But for a Froude number in between 1.7 and 2.5, it's a weak jump with small rollers. Uh, but when it increases up till the value of 4.5, it is an oscillating jump. Now it can unsteady, it can be unsteady, and it produces large waves downstream. But if the Froude number is in between 4.5 and 9, so it's a steady, well-balanced jump. This is a classic stable jump we often design for. But what happens when the Froude number is very greater than 9 value? So when the Froude number is greater than 9, it's a strong, rough jump that dissipates the energy very effectively, that can be intermittent. So it is very important to mention over here that the jumps can occur in non-rectangular channels and on sloping channels as displayed in this particular figure. So there are also submerged jumps as displayed in figure part B, where the tailwater is so high that the jump is pushed back towards the gate. So these are more complex and the fundamental physics remains the same. Now let us shift gears to another class of rapidly varied flow, which is the flow over the weirs. A weir is simply an obstruction on the channel bottom that the fluid must flow over. And because it causes a rapid acceleration and a distinct relationship between upstream depth and flow rate, it makes an excellent flow measurement device. So the most common type is the sharp-crested weir. It's a vertical, sharp-edged plate placed across the channel. The fluid flows over the sharp edge and springs free, forming a nappe. So the analysis is based on the simplified model. We assume that the pressure in the nappe is atmospheric, and we apply the Bernoulli's equation across along the streamline from a point upstream to a point in the nappe. So after integrating over the depth of the flow, we get an idealized equation. So because of the real world effects like viscosity, surface tension, and the contraction of the nappe, we need an experimentally determined coefficient. So for a rectangular sharp crested weir. The flow rate equation is represented over here, where in the H, capital H, is the weir head, which is actually the height of the upstream water surface above the weir crest, and B is the depth. The Weir coefficient C subscript WR is given by an empirical correlation, as displayed over here, wherein the PW is representing the height of the Weir crest above the channel bottom. But for a triangular sharp crested weir, or we can say a V-notch weir, the equation is a bit different, in which we have the huge advantage that because of the flow width decreases with the head, it can accurately measure the wide range of flow rates from very small to very large with a reasonable and measurable head value h. So the coefficient CWT is typically between 0.58 and 0.62 as shown in this particular figure. So moving towards the broad crested weir and underflow gates, we have the broad crested weir as displayed over here in this particular figure. This is a structure with a horizontal crest long enough that the streamlines becomes parallel and the pressure distribution over the crest is hydrostatic. The magic of this device is that for proper operation the flow becomes critical right on the crest. If the upstream velocity head is negligible, the specific energy upstream is approximately equals to h plus pw. But on the crest, at the critical condition, we know that E minimum is equal to 3 by 2 of the Yc, and Yc is equal to 2 by 3 of the specific energy. By applying the Bernoulli equation and using the critical flow relations, we derive a specific Q equation, volume flow rate equation, wherein the CWB is another empirical coefficient. Now, the broad-crested weir is robust and less susceptible to damage than a sharp-crested weir, making it very popular in field applications. So finally, let us look at the underflow gates, which is represented in this slide. These are the gates, vertical, radial, and or the drum, that control the flow by creating an opening at the bottom. Water flows under the gate as a supercritical jet. So for free outflow, the flow rate per unit width is given by small q equals to CD plus CD multiplied by the A multiplied by the under root G Y1. So where A is here is the gate opening, Y1 is the upstream depth, and CD is the discharge coefficient. The coefficient accounts for the contraction of the jet actually, which is the minimum depth downstream of the gate, where Y2 is less than the gate opening A. The ratio Y2 over A is called as a contraction coefficient, and CC C subscript C is represented in this figure. It shows how CD varies with the upstream depth ratio and the downstream tailwater condition. So we have covered very much of this particular topic. We have seen that rapidly varied flow encompasses some of the most interesting and practically important phenomena in open channel hydraulics. So hydraulic jump is nature's energy dissipator, allowing the supercritical flow to crash into subcritical flow in a controlled or uncontrolled way. And second one is that when we were studying the sharp-crested and the broad-crested vias, it uses the principle. It actually use the principle of critical or near critical flow to create a simple relationship between upstream head and the flow rate, making them invaluable for the flow measurement. And third one is the underflow gates that provide a meaning of controlling the flow and can also be calibrated to measure it. So each of these topics are very important for the fluid mechanics, and Today we have discussed each one of them in great detail. So this brings us to the end of our journey of hydraulics or the open channel flow. So we have gone from the basic definitions of the subcritical and the supercritical flows through the energy concept, uniform flow, gradually varied flow, and finally the rapidly varied flow. So you now have a solid foundation in the principles that govern the rivers, canals, and drainage systems. So thank you for your attention, and I will see you next time in some another course. Thank you very much.